Looking up at the night sky, we often picture the solar system as a perfect, predictable machine, a set of planets ticking along their orbits like the gears of a cosmic clock. For centuries, humanity tried to force a rigid permanence onto the cosmos. We drew maps with an unmoving Earth anchored at the center of the universe, surrounded by neat, eternal rings. Modern physics reveals a chaotic reality. The quiet, orderly layout we see today is just a brief snapshot in a violent 10 billion-year saga. Understanding our cosmic neighborhood requires tracing its entire life cycle, from its birth in a collapsing cloud of stardust to its inevitable disintegration. 4.6 billion years ago, the solar system was a freezing molecular cloud of gas and dust. Forces we are still studying caused that cloud to collapse inward, spinning faster until it flattened into a massive disk. Gravitational pressure at the center became intense enough that hydrogen atoms fused, sparking a nuclear reaction. This birthed the Sun, a star that instantly captured 99.8% of the system's total mass. This diagram shows the snow line, the thermal boundary dictating planetary architecture. Inside, the Sun's heat vaporized light gases. Only rock and metal survived, forming dense terrestrial planets. Beyond the boundary, freezing temperatures created massive icy cores that pulled in gas, forming giant planets. A planet's identity, whether a habitable rocky world or a toxic gas giant, was strictly dictated by its geographic distance from the newly born Sun. The early years of these planets were defined by extreme planetary migration and gravitational bullying. These tracks map the Grand Tack hypothesis. It suggests a young Jupiter plowed inward toward the Sun, clearing out the inner debris field, before the gravity of Saturn pulled it back to the outer system. That migration triggered an era of bombardment. Millions of icy comets and leftover rubble were flung out of their orbits, pummeling the inner rocky planets. Out of that violence emerged the stability we see today. The surviving planets finally settled into the predictable, quiet gravitational paths we now observe. Humanity is currently exploring the remnants of this quiet epoch. We send advanced robotics, like the Perseverance rover, to study the barren terrestrial surfaces of our closest neighbors. Our exploration extends all the way to the frozen, untouched leftovers of planetary formation in the distant Kuiper Belt, reached by probes like New Horizons. This current, stable architecture, the balance that makes life on Earth possible, is a temporary lull governed by the Sun's gravity. The solar system has a finite lifespan because the Sun's hydrogen fuel is limited. In roughly 5 billion years, that fuel will run out. As the Sun's core contracts, its outer layers swell into a red giant, expanding until it swallows Mercury and Venus. On Earth, this intense solar brightness boils the oceans and vaporizes our atmosphere, leaving a scorched, lifeless rock orbiting a dying star. Eventually, the Sun will shed its outer layers into the galaxy, leaving behind a white dwarf, a tiny, ultra-dense core about the size of Earth. This massive loss of solar mass weakens the Sun's gravitational grip. The mechanical balance of the entire system will fail. Over tens of billions of years, the orbits will unravel. Without a strong gravitational anchor, the remaining planets will destabilize and scatter, drifting away as rogue, frozen worlds in deep space. The solar system exists as a temporary, billions of years-long cycle of stardust borrowing structure before returning to the galaxy to begin again.